To see the answer here, you have to just realize that we're talking about a magnetic force acting on charges in this conducting rod, and that involves a cross product between the velocity and the B field. And here we have a velocity vector that's parallel to the B field, and we know that a cross product comes out as 0 in that case, and so no charge separation occurs at all. Notice that the magnetic force here is moving charge against an electric field. In other words, the magnetic force is in the opposite direction to an electric force acting on the same charges. And so the magnetic force is doing work because it's moving the charges in the direction that it's acting, and that is non-electrostatic work. Well, we already have a name for non-electrostatic work per unit charge. That's an EMF. And so the fact that we have a conducting object moving through a magnetic field has established an EMF across the moving rod. And that EMF is not really fundamentally different from what happens when we transport charge on a belt in a Van de Graaff generator, so that say, if you're turning a crank that's running the belt, you are doing work and establishing an EMF, or the work that's done in a battery that establishes an EMF across the battery. An EMF across a rod is all very well, but EMFs are most useful when they're in circuits, so let's arrange that. Instead of just a rod, let's look at a loop of wire moving through a magnetic field. And in particular, we're going to look at it going from a region of 0 magnetic field into a region where the B field is into the page and uniform, and then back out into a region of 0 field. Well, nothing happens as long as it's moving in the region of 0 field. But things start getting interesting as it enters the region of the field. So when just the leading wire, the front wire of the loop, is in the field, as we've already seen, that's going to cause charge separation in that piece of wire. Positive charges are being pushed by magnetic forces up to the top end of the wire, and so there's an EMF across the front wire, with a higher V at the top end and a lower V at the bottom end. Well, this is exactly like what would happen if there was a battery at the front end of this loop. And exactly the same thing will happen. A current will flow in the loop. In this case, it's going to go counterclockwise. Well, now later, the whole loop is inside the region of B field. Now there's an EMF across both the front and back wires. It's just like we'd set up this situation with batteries. And exactly the same thing will happen as if we did set up this situation with batteries, namely, nothing happens. There's no current flowing in the loop now. And now later, the loop is exiting the region of the field. There's no EMF across the front, but there is an EMF across the back wire. And so it's like this situation with a battery, and once again, current will flow in the loop, but now it's going clockwise. And finally, the loop exits the field, and we're back to nothing going on. While I'm comparing it to situations that we could set up with batteries, these currents are a little different to think about than currents when we drive them with batteries. And so we give them a special name. We call them induced currents. So we would say that we induced a counterclockwise current in the loop as the loop was entering this region of B field, and we induced a clockwise current in the loop as it was exiting the region of the B field. Note, though, that it's not just that a loop moving in a B field has a current in it. It doesn't, because when the whole loop was in this region of uniform field, there was no current whatsoever. So what is the common feature of the two situations where we do get current? The situation where it's entering the field and the situation where the loop is exiting the field. Well, the common feature is that the magnetic flux through the loop is changing. The flux is increasing as the loop enters the field, and the flux is decreasing as it exits the field. And so what we see is that a changing magnetic flux through a conducting loop will induce a current in the loop. And this is an informal statement of something we'll write down much more precisely later, which is Faraday's law. Well, we have an effect here which is connected to the velocity of the loop. And as with all such situations, it can be important to think about how it appears from different reference frames. So let's look at U in the Earth frame and Trogdor moving along with the same velocity as the loop. So from your perspective, the loop is moving, and it's moving from a region of 0 B field into a region of non-zero B field. But think about it from Trogdor's point of view. From Trogdor's point of view, the loop is stationary. It's the region of B field that's moving. So either the source of this B field is moving, or there are multiple sources and their behavior is changing, but either way, the way the field is distributed in space is changing. So according to Trogdor, the loop is stationary and the field distribution is changing. However, you both definitely agree that a current flows in the loop. For example, you could measure that the loop of wire warms up because of the current running in it. And so what you can agree on is that the magnetic flux through the loop is increasing. Whether you're in your frame or Trogdor's frame, you see that that magnetic flux is increasing. What this shows us is that if we have a conductor and we have a magnet, we can induce an EMF in the conductor by moving it, but we can also induce an EMF in it by moving the magnet. So let's see that. So I've set up a coil here with an ammeter, and if you look at the connections, you can see that this wire comes into the coil and goes around this way and eventually comes out here. And there is the positive connection to the ammeter. And so that tells you that if current is going counterclockwise around this coil, it's going to show up as a positive current. So now let's have a look at these currents that occur when you move a magnet in and out of a coil. So here is a rare earth magnet, and I've labeled the sides because you can't tell just by looking at them. And I'm taking the north pole and I am pushing it in and pulling it out, and pushing it in and pulling it out. And if you watch the ammeter, you can see it flickers, and you can also see that there are different signs. So now I'm going to flip around to the south pole, push it in and out and in and out and in and out. And if you look at that, you will have seen that the direction of the current changed depending on which pole I used and depending on whether I pushed it in or pulled it out. Overall, what this shows is that there are several equivalences here. Think about Trogdor's point of view, where the region of non-zero B field is moving. That could be achieved by having a great big solenoid that's being used to generate this B field, and it is moving, as shown in this diagram. Or alternatively, we could have a bunch of solenoids, and we're progressively turning them on and turning them off so that the region with the B field moves along. These will have totally equivalent effects, and so a moving source of field is equivalent to a changing field. But we also know that we get exactly the same effect if the field itself is not changing, but we move the loop, and so a changing field has the same effect as motion relative to a non-changing field. I'll just finish up with one more thing. When I moved the single wire through the poles of this magnet, I was getting potential differences of the order of a few millivolts, typically fewer than 10 millivolts. But now I have made a coil out of the wires, and when I insert and remove the coil, I get much larger potential differences. So we're going to be tending to look a lot at using coils and solenoids, and here's why they're so useful. Think about our moving loop one more time as it enters the region of B field. If it had a light bulb in it, then that light bulb would light up. We can use the EMF due to the motion of the loop through the B field to do work. And so it's just like the battery in another loop doing work to light up a bulb in the loop. Well, what if we have a coil connected up to the light bulb moving through the loop? Well, there's now going to be an EMF across each of these wires running vertically at the front end of this coil. And so this coil has multiple EMFs in it. It's just like connecting a whole lot of batteries in series up with a light bulb. And just like that situation, we're going to light up the bulb much more brightly. And so this is why coils are so useful in situations with magnetic fields. We get a multiplicative effect of the EMF that we get from moving the coil relative to a magnetic field.